Good morning, gentlemen. Today is Thursday, May the 7th, and today we are going to talk about section 13.2. Before we get any further into that, just a reminder that we're going to have a chapter 12 review activity tomorrow during your regularly scheduled class times. Anyway, over the course of the last few lessons, we've been talking about this idea of universal gravitation. And in section 13.1, we talked about this idea of a gravitational field. How far away from a planet do you have to be before you're no longer being pulled into it, right? The formula of Newton's law of universal gravitation, okay? And so when we talk about gravity, we usually think about gravity pulling us toward the center of a planet, all right? But in reality, and we stop when we hit the edge of the planet, right? But what happens if we didn't stop there? What happens if we were actually talking about going inside the planet? Now, remember when you were a kid and you were going to dig a hole all the way to China, all right, or wherever we are, wherever North America would end up on the other side of the world, all right? So let's say we dig this hole, okay, and forget about molten lava and the core of the earth and all of that other nonsense. Well, it's not nonsense, but you know what I mean. Forget about that for a second. And let's say that we really could dig a tunnel from here all the way to the other side of the earth, okay? Kind of like in this picture right here, all right? So you dig this hole through the planet. What happens to the gravity that you feel, the acceleration of gravity that you feel when when you're falling into or through the center of the earth? Well, it turns out that it's a kind of an interesting thing. What's going to happen is you'll start out up here at the surface of the earth and you jump into the hole, and there you go, all right? And initially you are going to accelerate with the acceleration of gravity, so about 10 meters per second squared. But when you get to be about a quarter of the way down, so right about here, that acceleration is cut in half. Now, what that means is that your acceleration is only 5 meters per second squared. Let me be very clear. That doesn't mean you're slowing down, okay? It just means you're not speeding up as fast as you did. It's almost like what we talked about when we were dealing with air resistance. A parachutist jumps out of a plane, and on his way down, his acceleration eventually becomes zero. That doesn't mean he's not falling anymore, right? But he's just not falling any faster. Okay. Now, so at this point, he'd be moving at about, or accelerating rather, at about 5 meters per second squared. All right. And eventually, when you reach the exact center of the earth, you actually have no acceleration. You're still traveling at a wicked speed, right? Because you've been accelerating at 10 and then 9 and then 8 meters per second squared, and you're increasing your velocity at an amazing rate. But once you get past the center of the earth, now everything above you is pulling you back up, and the stuff below you is pulling you down. When you're here at the top, everything is pulling you down, right? Because all of the mass of the earth here is pulling you downward. But when you're here, half of the mass is above you and half of the mass is below you. And so you're being literally pulled in both directions. And so as you approach the center of the planet, you will accelerate, but more and more slowly, because the center of the planet pulls you downward, but the part of the planet above you, right, if you're here, now about a quarter of the planet is above you. And so you're going to be pulled upward by a quarter of the planet and downward by 3/4 of the planet. Here, right in the middle, you're going to be pulled upward and downward at an equal rate, and so on and so on and so on. Okay? So what actually happens? Well, it's kind of an interesting aspect. You will continue to accelerate until you reach the bottom. Until you reach the middle here, and then you'll start to decelerate. Okay, and so you'll be literally slowing down as you go this way. And you'll just, if the earth is perfectly round where you're digging this hole, you'll just about reach the edge of the hole, all right, and then start to fall back down. And you'll go all the way up and all the way down and all the way down and all the way up and all the way down and all the way up. Now, in reality, there's going to be air in this hole. And so there's going to be a little bit of air resistance. And so if you jump, it's going to take you about 45 minutes to get all the way to this side. But if you don't grab the edge, it's going to take you another 45 minutes to go all the way back down. And by then, you may not have enough kinetic energy, the energy of motion, to actually reach the top of the hole. All right. And so what eventually will happen is you'll just oscillate back and forth and back and forth and back and forth. And eventually, you're going to be stuck, literally, right in the middle of the earth, because all sides of the earth are going to be pulling on you equally. Okay. Now that brings us to example number 4. So, and this deals with the illustration that we just were looking at. If you stepped into a hole bored completely through the earth and made no attempt to grab the edges at either end, what kind of motion would you experience? Well, the answer here obviously is an oscillation. You'd bounce back and forth. In physics, we call this a simple harmonic motion. All right, kind of like a pendulum swings back and forth and back and forth. You would be doing the same thing, up and down and up and down and up and down. And that's called an oscillation. And so you would oscillate back and forth, approximating what we call simple harmonic motion. Each round trip would take almost 90 minutes. All right, so it would take you an hour and a half to go all the way to China and back. Interestingly enough, you'll see in the next chapter that an Earth satellite in close orbit around the Earth also takes about 90 minutes to make a complete round trip. Coincidence? I think not. Anyway, so you experience an oscillation. Now, example number 4. Halfway to the center of the Earth, would gravity pull on you more strongly or less strongly than at the surface of the Earth? All right. Well, as we examined in that first slide we talked about today, all right, as you got closer and closer to the center of the Earth, your acceleration would actually decrease. It would get less. All right. And so gravity actually pulls on you less when you're near the center of the Earth than it does when you're at the surface of the Earth. All right, gentlemen. So that concludes our discussion of section 13.2. Please make sure that you've reviewed chapter 12 and you know all about Newton's universal law of gravitation. I will talk to you tomorrow.